Hello friends, and welcome to today's torque lecture. Torque is the return of the force. It's represented by the Greek capital letter tau. That's the squiggly T next to the torque. A torque is a force's ability to make something rotate. It turns out you can't make something rotate without applying a force, but the key to making it rotate is you apply that force at a location that's not the axis of rotation. All right, and if you do that, then you will get a twisting action. The equation for torque is given in the lower right-hand corner of the screen, and it is RF sine theta. R being the distance from the axis of rotation to the point of application of the force, F being the amount of force applied, and sine theta, where theta is the angle in between R and F. I'll show you what that is in just a second. That means that torque depends on three things. First, it depends on the amount of force. More force gives you more torque. Second, it depends on the distance between F and the axis of rotation. That distance we call R. Lastly, it depends on the angle in between R and F. The maximum torque exists when F is perpendicular to R. In other words, a 90-degree angle. Minimum exists when the force is in the same direction or away from the axis or directly toward the axis. So 90 degrees gives you a maximum torque. So we are going to rank the torques in these 5 different situations, A, B, C, D, and E. It turns out if you look at the wrench and finger C is pointing directly towards the end of the wrench, and it isn't going to cause any torque at all, because R is from the axis to the point of contact and F is from the point of contact back towards the axis. That technically gives you an angle of 180 degrees, and you all know from trig that sine of 180 degrees is 0. So C is going to give you 0 torque. Next is D. D is going to give a small torque for 2 reasons. One, D, the finger is close to the axis, and farther means more, so closer means less. But also the angle in D is not a right angle. And anything less than a right angle gives you less than optimal maximal torque. The next letter is A. A is at a right angle, but the force is still applied very close to the axis of rotation. Next is B. B is like A. It's at a right angle, but the force is applied farther away. And of course, the biggest torque is applied by E. And the reason is this torque is at a maximum distance away from the axis of rotation. This person is the strongest in the force, and of course, this torque always is right in his choice of angles. All right, and that is it. Sorry, that's my joke for the day. Moving on. Steps for torque problems. In most problems, you have more than one force applying a torque. So if you have that, you're going to need to draw what is kind of like a free body diagram, except now we have to draw the actual body rather than just a dot. So step 1, draw the rotating object and label the pivot point. We're going to draw the entire object now, because you have to show where on the object the pivot point is occurring. 2, we're going to label the forces acting on the objects, just like we did with free body diagrams, but the location of where the force applied actually matters now. Number 3, if the object is not experiencing angular acceleration, in other words, if the object is stationary or rotating at a constant speed, you can set the torques counterclockwise equal to the torques clockwise. Of course, if it is experiencing angular acceleration, you go the winner torques minus the loser torques equals I alpha, but that we'll save for the next unit. All right, so all the examples that we're going to be doing in this particular unit are static equilibrium examples. Static means not moving. Static equilibrium means not moving and forces are balanced. I know that statement is redundant, but here's what it means. Static equilibrium means no translation, meaning no motion up, down, left, right, forward, backwards, and also no rotation about any axis. And if that's true, no translation means the net force in the x, the y, and the z directions are all 0. That means you could potentially write 3 equations. We're only going to be doing 2 equations, the x and the y, this year. Then you could also say the net torque is 0 about any axis. Now here's the beauty of it. Because the object is not rotating, you could pick any axis you want to be the axis of not rotation. All right? Case in point, this hanging sign. All right, in the case of the hanging sign, that sign, we're going to choose the sign itself as the mass. All right, we are going to label all the forces on that mass. We've got mg pointing down. We've got the tension in the cable pointing up and to the left. And if that's all you had, if you just had a down force and an up and to the left force, you would realize that sign would be accelerating to the left unless there was some other force, and there has to be another force. If the wall weren't there, the sign would swing in toward the wall. So therefore, the wall must be pushing the sign outwards to the right to balance the left force in the tension. All right? But also, if you were to choose an axis of rotation, say in the middle of the sign, and there were a force up from the tension and down from the sign, that would mean the sign would be slipping and falling down, twisting counterclockwise. So there must be an upward force from the wall to stop that from happening. So therefore, there are a total of at least 4 forces. Tension up and to the left, the wall pushing up and the wall pushing to the right, and the weight of the sign hanging down. Once you have those 4 forces labeled, then you can do an x force balance, which is force of the wall in the positive x direction minus the force of tension in the negative x direction equals 0. You could do a y force balance, which is the force of the wall in the y direction plus the force of the tension in the y direction minus the weight of the sign equals 0. Now here's the beautiful thing. If you were to pick an axis of rotation at the point of contact between the sign and the wall forces would be acting at the axis of rotation and therefore would provide 0 torque. So if you pick that location, and you can pick any location you want, but if you pick this location, you can ignore the effect of the wall forces on the torque. So all you're left with is the hanging weight at a distance of 0.75 meters and the tension at a distance of an R value of 1.5 meters. So the equation for torque, net torque, becomes 0.75 times the weight of the sign times sine of 90 degrees, and that one's a clockwise, therefore positive torque, minus the tension. So 1.5 meters times the tension times the sine of 20 degrees equals 0. And then you could solve that for tension. You don't even need an x or a y equation to solve for this tension. And that's it. Number 2, teeter-totter. You're going to see a lot of these. How far away must the older boy sit from the center of the teeter-totter? To do this one, you could write an x-force equation, but there aren't any x forces. So we're going to ignore that one. All the forces are in y direction, so you could write a y force equation. I've said the y forces are the weight of the baby, the weight of the larger child, both of those forces push down, and then of course the teeter-totter itself is supported by an axle of some sort, a pivot point, I'm going to call that a normal force, upward. All right, so the normal force up minus the mass of the baby times g minus the mass of this larger child times g equals 0. Okay, but none of those give me what I'm looking for, which is how far must the larger child sit from the axis of rotation. So to get that, we have to use torque. I'm going to choose an axis of rotation at the pivot point of the axle. You don't have to. Assuming this is a static equilibrium question, you could put the pivot point anywhere you want, but I'm going to choose the middle of the teeter-totter. And if I choose the middle, that means the normal force, the torque from the normal force can be ignored because it's acting at the axis of rotation. Therefore, I have the baby causing a counterclockwise or negative torque, and the larger child causing a clockwise or positive torque. So I have minus 2 meters for the baby times the mass of the baby times g times sine of 90 degrees. Then the other term for the larger child, that's a positive. The radius of the larger child times the mass of the larger child times g times sine 90 equals 0. Plugging in numbers, then you can solve for the radius at which the larger child is sitting from the middle. And that's it. We are going to see lots of different example problems in this unit. I have a number of them. These are common torque scenarios. What I'm going to do for these ones is I'm not going to work out all the math, but I'm going to show you how to draw arrows and how to build an equation from the arrows you have drawn. The first one is a beam sitting on 2 scales with 2 people sitting at different locations on that beam. This is generic. There are a total of 5 different forces that I can think of. The 2 normal forces from the scales, the 2 weights of the 2 people, and I also threw in the weight of the beam itself that they're standing on, because I'm assuming that if it's big enough to hold 2 people, it has a significant amount of mass. All right, I chose as my axis of rotation the left end of the beam. You don't have to choose this as your axis, and maybe it would be smarter not to, but you can choose whatever you want as your axis. It doesn't matter. If you choose, say, the location of the first scale as your axis, then you could ignore that normal force in your torque calculation. But I put it all the way to the left side because it was a little bit easier to draw. And here we go. I said there are no forces in the x direction. There are 5 forces in the y direction. Normal force 1 and normal force 2 from the scale are both positive. Then the weights, all 3 of them, are negative. Then, since I am always measuring from the end of the stick in this case, I have a negative torque from the first normal force. I have a positive torque from the first person's mass. I have a positive torque from the weight of the balance beam. I've got a negative torque from the second normal force, and I've got a positive torque from the second person's mass. All right, and you can see, I'm not going to recite back the entire equation I have derived, but it has 5 different torque terms in it, and there they are. All right, going down the list, every single one of these questions, you can say net force is 0 in the x, net force is 0 in the y, and net torque is 0 about any axis. I've chosen for the tipping point question the axis of rotation to be the tipping point, which looks to be a little bit off center. It actually needs to be a little bit off center or else the thing will fall. The second that center of mass of the balance beam goes over the edge, you'd have 2 torques clockwise, or actually you'd have 3 torques clockwise, and that would cause the thing to tip over. All right, so in order to not tip, the weight of the balance beam needs to be to the left of that corner. I chose my axis of rotation to be the corner itself, but you don't have to. I just did that for this problem. For the ropes question, There are a total of 4 forces, 2 normal forces. Oh, those are not normal forces. Those are tensions. Tension in rope 1, tension in rope 2, and then, of course, 2 weights hanging down. No X forces, 2 positive Y, 2 negative Y, 2 positive torques, 2 negative torques. And again, this is a slightly modified version of the hanging sign problem. Force of wall in the Y direction, force of wall in the X direction, a tension diagonal, and this one actually has 2 weights, the weight of the beam plus the weight of an additional hanging mass. And I will leave it to you. Once you have these once you have all the arrows drawn, then you can build equations from it. Once again, for the hanging sign, usually the easiest way to do this one is to use the axis of rotation at the point of contact between the beam and the wall. But you might want to do something different depending on what you are given and what it's asking for in the problem. All right, and that's the end of this lecture. Thank you.